Hey everyone, this is Dr. Walker. Up to now, we've been talking about potential energy and potential difference, and we saw the relationship between the two, that when a charge moves through a potential difference, its energy changes. Now we want to look at the relationship between voltage and electric field. So let's do that here. First of all, we learned back in video 518 an expression for potential energy. We learned that the change in potential energy of a charge as it moves from one point to another in an external field, we said that change in potential energy was equal to negative Q integral of E dot ds, where ds is a displacement vector. So from this, we can easily derive an equation for voltage related to electric field because we know that potential difference is potential energy per charge. So all we have to do to get potential difference is divide by Q, and we get negative integral of E dot ds. So there we have it. The relationship between the electric field and the potential difference. You have to do the dot product of E and ds. And in this case, right, we divided out the charge, so there does not have to be any motion of a charge for us to find a potential difference. We can just have 2 points and find a potential difference between them by going from one point to another, and that path, that is what has all the little elements ds along that path. Let's apply this equation to the general case of having a uniform field, just like we did earlier when we were looking at potential energy when a charge was moving in a uniform field. So let's assume that we're looking for the potential difference between 2 points, A and B. We don't care about this charge here. We don't have to look at it. It just happens to be in this picture here. But let's say we have a point A here and a point B here, and they are a distance d apart. So to find a potential difference between those points, we would do the integral negative E dot ds from A to B. We want to integrate along that path. So if we're going in a straight line, and later we'll see that it's independent of the path, but for now, let's assume that we are moving along the field, then what this means is that the angle theta is 0, right? We have E ds cosine of 0. I can go ahead and write that down. We have E ds cosine of 0 if we're moving along the field. And that means that since this is 0 degrees, then that we get negative E and the integral of ds. So we're just integrating along the path from A to B, and the distance from A to B is just d in this case. So we get delta V is negative ED. And this should come as no surprise because we found back in video 518 the expression for the change in potential energy of a charge. If we remember, in a uniform field it was negative Q ED. So no surprises here. And then the next thing I wanted to point out is that we notice that we do have a negative. I could have pointed out in the previous slide as well, but we do have a negative, and that is significant, right? It reminds us that the electric field lines point in a direction of decreasing potential. The electric field always points from a high potential to a low potential, and so that's why when we draw these plates, we'll usually draw positive plates for the higher potential and a negative plate for the lower potential. And they could both be positive, it doesn't matter, as long as VA, in this case VA, is greater than the potential at VB, at B. Let's look at a question. A negative charge is moved from point A to B. What happens to its potential energy And I actually meant to change this question. I forgot to write it down on here, but what I meant to ask, forget about this question, is I meant to ask, where is the potential lower or higher? Let's just rewrite this. Where is potential lower? Because we already looked at potential energy earlier, so I meant to change this question. Just a little typo there. So is it potential lower at A or at B, or are these 2 points at the same potential? So think about it, pause the video. So according to what we just learned, the electric field always points towards a decreasing potential. So that means that the point B here is at a lower potential. So here we once again have the potential at A is greater than the potential at B. Let's go ahead and look at this question just since I did have it here. If we do have a negative charge that is moving from A to B, so it's going to a lower potential, then what's going to happen to its potential energy? Well, go ahead and pause the video. There's a couple ways to do this. I would think the easiest way to do it is to use the equation that the potential energy is Q dot delta V that we learned back in 518. And now that we know that the potential difference is negative, because we are going towards a lower potential, then we can just say, okay, the Q is negative, the delta V is negative, so that means that the change in potential energy of the charge is positive. And that agrees with what we talked about before, that the charge does not naturally want to go down. That means that there must be some external force pushing it down, doing work on it, and increasing its energy. The last slide here is just a quick summary. We have been dealing with a bunch of different terms, and they all kind of sound the same. We have potential difference, and change in potential energy. So just a reminder of the difference between these three terms. So V is called electric potential. Sometimes we drop off the electric and we just say potential. That's the potential at a point. So all charges produce a certain potential at a point. We'll discuss that more in depth in the next video. But you don't have to have a charge at a point. Just like when you're measuring electric field, you don't have to have a charge at that point. There is an electric field at this point. There is a potential at this point. Towards here near the positive plates, we have a higher potential than near the negative plate. Okay, so the next term is potential difference, and that just means the difference in potential between 2 points. So if you know the potential at one point and the potential at another point, then you can find the potential difference between those 2 points. Again, you don't need any charge there. And this electric potential difference is often just called voltage. And then the last term is the change in potential energy. So I like to think of this as what I said earlier. When a charge moves through a potential difference, then it will experience a change in the potential energy. So for energy, you have to have a charge, right? System of charges to have energy. A point does not have energy. But so for this one, you visualize your charge moving from one point to another in a potential difference, and then you can use the equation delta UE equals Q delta V to figure out what is the change in potential energy of that charge as it moves through that potential difference.